All right, welcome back, folks. I hope you had a great long weekend and got fully recharged. So let's get started. Last time we were talking about the development of optimization algorithms, and we sort of briefly go through the developments in the early times, like the traditional methods developed by those giant guys in the history, like gradient descent developed by Cauchy in the 18th century, and the well-known Newton's method for both solving nonlinear equations and also solving optimization. And we will talk about convergence rate of Newton's method today. And also for solving problems with constraints, you can try to dualize the problem, make it unconstrained, and this involves using Lagrange multiplier. Well, in the last century, optimization algorithm gained great development, especially after World War II. During World War II, the logistics for military operations was a big headache, especially for the UK. So people there tried to develop methods systematically how to do operations in a smart way. And this comes to this was the origin, the beginning of operations research, the whole subject. And in particular, linear programming was developed in this time. So like von Neumann and Kontonovici, those are the pioneers in this area. And also Kontonovici won a Nobel Prize in economics in 1979. Part of the prize was given for his work in linear programming. And this is highly related to optimal transport in the discrete setting. The method, it was difficult to solve linear programming at that time, while later George Danzig, he developed the well-known simplex method, which was very fast, but in terms of complexity, there was no theoretical guarantee. So there's no guarantee how many polynomial time you can solve my problem in linear programming. Because in simplex method, you need to check, in the worst case scenario, you need to check each vertex of your polytope. And in n dimension, the polytope could be, there could be exponentially many vertices in terms of dimension n. So there could be 2 to the n number of vertices. If you want to check one by one in the worst case scenario, then you need to do 2 to the n operations. So this is exponentially large, but we want something polynomial. So even though the method was very successful in practice, but there is no theoretical guarantee, no complexity. Well, later in the 1970s, Kachin from Russia, at that time he was from Soviet Union. So he proposed, he didn't propose, but he proved that ellipsoid method can give you a polynomial time guarantee in terms of dimension. But this method was not that successful in practice. So there's a trade-off. Simplex method was good in practice, but not good in theory. Well, on the other hand, ellipsoid method was successful in complexity. There's a guarantee in terms of polynomial convergence, but in practice, this method was slow. So later in the 80s, Kamaka from IBM, he proposed the interior point method. And this method has the best of both worlds. It was both theoretically, there is a theoretical guarantee, it is polynomial time solvable, and also in practice, this was much faster than ellipsoid method. And in many cases, it's also faster than simplex method. Interior point method can not only be used to solving linear programming, but it can also be applied to like quadratic programming, semi-definite programming, second-order Cohen programming. It's very successful in practice. Many of the optimization solvers, so for example, Groby is using interior point method for solving many problems. It is very successful in business applications. So this was in the 20th century, and after the development of interior point method, many people in this area work on the application and the theory of interior point method. Basically, this is a second-order method, and our focus in this course is for first order method. So let's see what people have done recently. What people have done recently in the last 20 years. So these applications were about first order method. The reason is that at that time, like in the 1980s, 1990s, the problem was not that big. So it's like a middle-sized problem. Maybe your discernible is in dimension in like 1,000 or 10,000, but it's not that big. So it's solvable if you use, it's doable if you use a second order method. But recently, in the age of machine learning, the problem gets a huge scale or extremely huge scale. So the dimension could be millions. So it's not suitable to use second order method because if you work with the Hessian matrix, that's very expensive, computationally speaking. But if you work with just a vector, like a 1 million dimension vector, that's still doable. So recently, people are more focusing on first order method. In the first 10 years, first decade of the 21st century, people have been developing all these methods. And particularly, people were very interested in the old methods that were developed 50 or 30 years ago, and they want to see their applicability in the huge scale optimization problems. For example, Frank-Wolf, which is a gradient-free method, which is a projection-free method. As we mentioned before, projection onto some convex set could be expensive. So people were interested in what if we do not want to do any projection? What if we just stay in the feasible region? So this is a quite famous algorithm in machine learning recently, but it was developed more than 60 years ago. And ADMM is suitable for solving distributed optimization. Suppose you have your data distributed in several agents, and you want to keep the data locally. How do you do this computation? So ADMM developed in the 50s, and it was developed in the 50s initially for solving partial differential equation. So it's originally from it's originated from a numerical scheme for PDE. But later in the 70s, people used the same idea, the alternating direction method, for solving optimization. Initially, in the 1950s, this was called ADI, alternating direction implicit scheme, if I don't remember wrong. And in the 80s, this guy Nesterov, we will talk about this name Nesterov again and again in this class, and he was one of the authors of the textbook I recommended, the yellow one, Lectures on Convex Optimization. He's a giant in optimization algorithm. This guy is very brilliant. He proposed several interesting algorithms, which is both theoretically provable and also practically fast. So one of the big achievements of his works is fast gradient, which is Nesterov accelerated gradient. This is the first method that achieves optimality in convex smooth optimization. As we mentioned before, gradient descent is not optimal, but accelerated gradient is optimal. So this was his work in the 80s. But at that time, people didn't realize the importance of this method because at that time, people were fascinated by the integral point method that was in the 80s. Well, later, around this time, 2009, this method gained more attention because we are solving huge scale optimization problems. Second order is not doable. You need to use first order, and in first order, this is one of the optimal methods. So that's why accelerated method is now very famous. So recently, these two actually, the first, second, the third, and the fourth, Nesterov contributed a lot in all these methods. And this one, Fista, this was developed by two mathematicians in Israel. Well, this is a variant of Nesterov's accelerated gradient method. So this is not new, but all the other methods are new, and I think they were all invented by Nesterov. And the other guy I want to mention here is Nemirovsky. he's like the founding father of modern convex optimization. He also in optimization algorithms. He also proposed several interesting algorithms. For example, he was the developer, one of the developers of the ellipsoid method, but he didn't prove. I think he didn't prove the polynomial time complex convergence. But later, Kachin proved that this one is solvable in polynomial time. And also, Nemirovsky also proposed the mirror descent. So we will also talk about mirror descent in this lecture. And these two guys, they worked together not only on interior point methods in the 90s, but they also proposed one of the most interesting algorithm for solving convex non-smooth problems, which is called the bundle level method. But we will not talk about that one. The analysis there is not suitable for this class. But that's one of the famous algorithms the two giants proposed. Okay, so now let's talk about some applications of the optimization method in machine learning. So before we jump to the new topic, is there any question? Yes.
Just curious if there's an intuition behind why the simplex method works reasonably well in practice, even if there's no theoretical guarantee.
Oh,
It's like,
yeah, that's a good question. Because when we say it's not good, it's not polynomially time solvable.
right.
That's big. So you need to first give me the definition. In which case you are talking about the complexity. We were talking about worst case scenario. So I think in all the complexity we're talking this class will be worst case scenario. So you are like very risk averse. But so that's the case when simplex was not good. In worst case scenario, you could check at all the vertices. So there could be exponentially many in terms of dimension. But in average case, simplex is polynomial time solvable. So there was an interesting work by Shanghua Teng and Daniel Spielman. Shanghua Teng is from he's now at the University of Southern California, and Daniel Spielman is in Yale University. So these two computer scientists, they were also curious about this question asked by you. So they tried to answer this question in around 2004. So they first proposed a notion of average case complexity, and then they analyzed the simplex method, and then they show simplex is polynomial time solvable in the notion of average complexity.
And is ellipsoid exponential? I guess to ask kind of the opposite question about ellipsoid, like if there are, well, I guess that of course it's not exponential, it's polynomial.
In worst case, it is polynomial, so in average case, it's also polynomial. So in the average case scenario, you need to think about the distribution of your problems. So that's how you take an average, try to do an expectation. But it's a very complicated analysis.
I guess, yeah, is ellipsoid worse than simplex in average case? Or has anyone looked into that?
To be honest, I don't know the answer, but I believe, at least in practice, people are more interested in this one. So probably, I'm not sure. Maybe nobody studied this one in average case, but I cannot say for sure. Any other questions? Okay, so one of the topics in our class is stochastic optimization. And this is so many problems in machine learning can be formulated as stochastic optimization. For example, the population risk minimization is an instance of stochastic optimization. So here is your loss function, and you want to take an expectation over the distribution of U and V. U here could be the feature, and V here could be the label. So here we are taking an integral over your PDF. But taking integral could be very difficult in practice. It's intractable, for example, when dimension is greater than or equal to 5. In most of the case, this is intractable. So we want to take an approximation. This is one of the approximations that we will use for solving stochastic optimization. It's called sample average approximation in abbreviation is SAA. And there is another approximation called stochastic approximation, and we usually just call it SA. So in SAA, you just take a large number of samples. Here we take little m samples, and then you just, so here we just naively assume the distribution is uniform. So we just take the simple average of them, and this will be the approximation to this population risk minimization, and this is called empirical risk minimization. In this case, many machine learning problems are in this form. For example, regression or classification. For example, SVM can be written in this form if you specify the loss function. This is one of the formulations for SVM, support vector machine. And the most basic algorithm to solve this problem is stochastic gradient descent. So instead of using here I think okay, yeah. So instead of using the true gradient to this one, we use a stochastic gradient. But in this case, the randomness is coming from here. It's coming from the samples you take. And this is the basic gradient step. Basically, what's inside the bracket is a gradient of this one. Right? This is the gradient of the loss function, and here is the gradient of the regularization term. This is just to give you an idea what how to solve stochastic optimization, for example, from a machine learning application. But we will see more rigorous analysis and more interesting problems later on. And we will not only, so this is, as we mentioned, this is not the only option you have for approximation. You can also do stochastic approximation. That is a totally different approach. Here you try to, so after you do this approximation, the problem becomes totally deterministic. So after that, after you do this approximation, you just apply any algorithm that you want to try from deterministic optimization to this problem. So there is no randomness at all. The randomness are hidden in the samples. So the problem here is deterministic. For example, when we solve maximum likelihood estimation, MLE, we are using this approach. Well, the other approximation is different, stochastic approximation. In that problem, we do not take all the samples in the beginning, but we try to do it in an online fashion. So this is more like offline. You take all the samples and then solve it offline. But in the other approach, SA, it is totally online. So as you solve the algorithm, you try to take a new sample, and then use this new sample and do an estimate of the gradient. So this is a stochastic gradient. So this one is not, I think stochastic gradient descent is more suitable for using SA, not SAA. So here is not very precise. So in the other case, you take a gradient, stochastic gradient at the previous the previous search point xk. So you take a gradient. So previously you were at the point xk, and then you take a gradient. This is a stochastic gradient. So this is my stochastic gradient. The stochasticity is described by this sample CK. And then with this stochastic gradient, I'll do my gradient step. So this is stochastic gradient descent, SGD. Sk plus 1 will be xk minus lambda k. Lambda k is the subsize that you choose at this iteration. So you can view this bracket as an instance, as an example of this one. But we just do we just take one sample. So it's like we take UIVI. UIVI is like a CI. We just take one sample of the distribution. It's hidden in this KCK in SA. Another interesting example is sampling. So in this class, if time permits, we will try to cover a little bit about sampling. But in any way, the take-home message is that sampling problems is very much similar to optimization, but it's just in a higher dimension. It's in infinite dimension. Other than that, beyond that, there are also many interesting connections between the two, not only from the problem itself, but also from the algorithm design. You can also try to mimic what we do in optimization and translate it into sampling. And probably with high probability, it will give you a very practical algorithm. The sampling problem that we are interested in is like this. So here is a PDF, probability density distribution. And given this PDF, which we call nu of x, and this is proportional to exponential to the negative f of x. For example, the Gaussian distribution can be written as e to the minus quadratic function, and the exponential distribution is e to the minus affine function. So many distributions can be written in this form. And we are interested in taking a sample from this distribution. It is very useful. Sampling is very useful in many cases. For example, in MCMC, Markov chain, multicolumn Markov chain. In MCMC, you want to take a large amount of samples, and then you can do some post-processing. That's the study in MCMC. But before that, I want to have the ability to sample even a single data point. But in many cases, this could be very challenging because this function f, this potential function f, could be very nasty. Suppose I give you a distribution like exponential to the minus, this is L2 norm minus L1 norm, maybe 3, and something like this. This could be very nasty, and taking a sample of this one is not easy. So you need to design some algorithm, try to do a sampling for this distribution. So sampling one data point could be challenging. And it's interesting that people discovered that this sampling problem can be written as an optimization problem in infinite dimension space, which is the probability space. So you can view every probability distribution as a infinite dimensional vector because you can view, for example, a normal uniform distribution in n dimension could be something like this: 1 over n, 1 over n, 1 over n, and in total you have n elements, right? And you can just view this one as a discretization, but in continuous space or in probability space, this could be an infinitely long vector. But all the numbers sum up, they are non-negative, and sum up, they will give you just 1, right? So this can be viewed as an infinite dimension vector. So you can view all the probabilities as a point in a vector space, but this vector space is just infinite dimension. It's a probability space. So we are minimizing over the probability space. So V is coming from the new. Yeah.
You can view this as a vector even the probability is continuous.
Yeah, you can view it as a. This is just for you to understand, but it's not really not a vector.
Oh, okay.
It's just to view it as a vector. So this is from the probability space. Nu is a distribution, and here h nu of rho. H nu of rho is a relative entropy. This is a notion from information theory. So here, both nu and rho, they are distribution, PDF. And this is an integral in this form. So this will give you a real number. This is called the relative entropy, or KL divergence. So this is something we want to minimize, but our decision variable is not a finite dimension object, but infinite dimension. So the gradient flow to this problem is the Fokker-Planck equation. This is like the optimality condition in optimization. You can usually write a gradient flow for the problem. So basically the gradient flow is the optimality condition is like this part is 0. So in optimization, when I want to minimize f of x in the whole space in Rn, I can, if this one is continuously differentiable, then I can say my optimality condition is gradient of f is 0. And the gradient flow of this one is just dx dt. This is an ODE, ordinary differential equation, is gradient minus gradient f of x. And here, this is so here basically we are mimicking the gradient flow for optimization, and this is gradient flow for the sampling problem. But this one, so here it describes how the distribution rho t evolves with time. So can view this rho as a function of t, and both the time t and the space x. But so basically rho is a distribution. So for example, initially rho, if you want to solve this PDE, initially rho could be this one. You begin with a Gaussian distribution, and in the end you want to find something maybe very nasty. This is rho infinity, and then in the middle you could have some rho t, and this basically this PDE is describing how the rho t evolves with time t. So along this time axis t, there will be many different rho t, and we want to see how the rho t looks like, because rho t is a distribution, is a function basically, it's a distribution. So if you fix a time t, it's a function of x. That's what this PD is describing. Well, because rho t here is in the probability space, but we cannot track rho t because you do not know you cannot track something in probability space. That's very difficult to do. So you want to go back to Rn, and this is what we do in Rn. So continuity equation of Langevin dynamics can be shown to be Fokker-Planck equation. Basically, this is saying that if in Rn space I want to follow a point xt, so xt is a trajectory. If I can follow this point xt, then I can follow the rho t in probability space, because this xt it follows the distribution of rho t. So if you fix a time t, then the x is a random variable, right? X is just random variable, and this is distribution. This is saying that with a fixed t, this random variable is sampled from this distribution. So if I can follow xt in Rn, then I can follow rho t in the probability space. So this is something we try to do because we cannot do operations in infinite dimension space, but we can do in Rn. Well, this is still very good in the sense that this is continuous, because this is a differential equation. It's continuous. When you implement the algorithm, you always want to discretize. So this is the discretization of Langevin dynamics. And this is called unadjusted Langevin algorithm. So you can, let me write the algorithm here so you can compare with SGD. The algorithm looks very similar to SGD. So ULA So they are both iterative methods. Iterative means that given xk, I want to do some operation to find the new search point xk plus 1. So you can do this one again with k replaced by k plus 1. So this is an iterative scheme. In ULA, you want to do a similar thing. So with the previous search point xk, you want to do a gradient step, then you want to return the new search point. But this part here is deterministic. eta k is another step size, just like lambda k. And this is the gradient that you take for this potential function. So you can view this f as the f in optimization. But here we inject some noise. This z is a Gaussian random variable. And you can view the whole thing here. So if you divide by eta k. And then the whole thing in the parentheses is just like this random, this stochastic gradient. So basically, they are doing the same thing. So you can view this ULA as a, so basically we are trying to mimic everything in optimization and try to do it again in sampling, right? And so here is what we do. You reformulate the sampling problem as an optimization. So you mimic the problem. And now you are trying to mimic the algorithm. This is the algorithm we have in stochastic optimization. And you try to mimic this one, and then you can design this ULA. It is a counterpart of the SGD in sampling. And you can even do something more innovative. Yes.
Would you please go to... would you please explain the relationship between those three items one more time, the gradient, flow, continuity, and discretization?
So this one is describing the gradient flow is describing how the rho t evolves a long time.
Yes.
Because rho t is a distribution. In the beginning, you start from some rho 0, right? You begin from some rho 0. That's like when you solve the PD, you also need to give your boundary condition and the initial condition. This is like your initial condition. So my initial condition looks like this. Rho x0, because it's rho of x comma t, right? This is rho 0 of x. This is my initial condition. You begin from some distribution rho 0, and in the end you want your rho infinity of x to be nu of x. Nu is your target distribution. You want rho t goes from rho 0 to rho infinity. But along this process, I want to know what my rho t looks like, right? There is a evolution, right, of rho t. So this is describing how rho t evolves.
By optimizing the function, we are evolving from an initial distribution to another distribution that we're going to. Yes.
Yes, because this is rho t. Sorry, this is a mistake. Here is rho, not nu. Sorry.
Yes.
Yeah, nu is fixed. Nu is our target. Rho is what we are minimizing with respect to. Sorry, this is rho. Yeah. So we want to know how rho evolves. Just like in optimization, you want to know the trajectory of your x, and that is in optimization the trajectory of x is described by an ODE. That is the gradient flow for optimization. And here we just want to mimic, and the gradient flow, the trajectory is an PDE. And here, because it's not easy to track something in infinite dimension, so we want to track something in finite dimension in Rn. And this is what we track. Because you can show that if you follow this ODE, then the distribution of xt is rho t. So you can also follow the distribution, the rho t in probability space. And how do we follow xt? This is by discretization, and this gives you the algorithm.
Great, thank you very much.
Any other question? Yes.
Why do you have that Brownian motion for that ODE?
Here?
Yes.
Because you need to have some randomness, basically. And this randomness is coming from here. Or you can see more precisely, it comes from the delta rho here. So if we have nothing here, if it's just 0 here, partial rho, partial t is delta. It's not Laplace rho. This is heat equation. And the solution to heat equation is dx is equal to this part. Basically, the solution to this part is described by the gradient step, gradient part. And this is a solution to the heat equation. This is a diffusion process because we are, you can even start from a point mass. So rho t could be a delta function at a certain point x0. So you can begin from a point mass and try, and with this diffusion process, you can push all the property mass to other places, right? So initially you are from a point mass, and later on the property mass is everywhere, but there it follows a distribution. Yes.
You have the standard normal distribution here because of the standard Brownian motion.
Yes, yeah. The discretization of this one gives you the Gaussian variable. Okay. So beyond mimicking the SGD, we can even do something more interesting. In optimization, there is a powerful framework, which is also one of the topics in our class, the proximal point framework. Basically, you do not want to minimize f of x directly because that's difficult to do. For example, in convex non-smooth optimization, minimizing fx directly is very challenging. So you want to do something more tractable. So you want to minimize f of x something like this. So suppose I have a search point xk. I want to find my next search point. So this will give me a next search point xk plus 1. With this xk, I can build some regularization, right? I can have this quadratic regularization. Basically, this is saying that I don't want my next search point xk plus 1 to be very far away from xk. That's what I'm penalizing here, right? I'm penalizing the distance between the two. So this gives you the name, proximal point. You want to find a nearby point. You don't want to go very far away, right? If lambda is small, then your penalization is very strong because when lambda is small, this number here, 1/2 lambda, is very large. So you want to penalize it because if this is large again, then the whole thing will be very large. But this is it's against our adjunctive minimizing. We want to minimize the whole thing. So we do not want this part to be very large. That's the goal. We want to find a nearby point. So you want to, with this xk plus 1, you can build another subproblem. So this will be lambda k plus 1, xk plus 1. And you want to do this whole process again and again. So it's something like this. Initially, you are from x0, right? And you want to maybe look for some third point in this region. And you find the next point here, x1. So you build another. So this is just some explanation, but not very precise, right? And with this x1, you want to find the next point in this region. And next step, you find this x2, and you go on and on. Right. So every time you just take a very small step. So that's why this lambda k is also called step size, because xk plus 1 can be one way to solve this one is by gradient descent. And what you do is basically just take this step. So this is the step that you take along the negative gradient direction. So that's why lambda k is also called step size. This is a very powerful framework. Many of the first order methods we want to cover in the class, there are instances of this framework. For example, gradient descent, stochastic gradient descent, accelerated gradient, Newton's method, Chambly-Polk for solving saddle point problem, ADMM, and proximal bundle method. So all of these algorithms are proximal point framework instances. So once you have the analysis, the proof for the convergence of proximal point, you can apply it to all these algorithms, as long as you can show each of them is an instance of the framework. So you just need to show why gradient descent can be viewed as these two steps. So this is just one step, and you need to do this recursively, right? This is an iterative method. So in the first step, basically, you're just changing the proximal point. You just change the, basically this yk is like xk here. So it's just this algorithm. This is a one-line description, but this is a two-step description. The reason why I want to do two-step, because in sampling, this step is not, it's again easy, but it's not that simple. So in sampling, in optimization, you want to minimize f of x. In sampling, you want to sample from e to the minus fx. here we use proportional tool. The reason is the constant, the normalization constant is not important in sampling. So here, if you want to write new relay as a PDF, you need to have a normalization constant, right? This is e to the minus ff(x) divided by the integral, right? You need to normalize so that the integration of new x is 1. But we just ignore this constant because that's not very important. The reason why this is not important is just like you minimize f of x. If I have a plus c here, c is a constant. It's not important to find the solution. Right, so that's the reason why we don't use equal to, but proportional to. In sampling, you can also try to do some similar thing. Here we have 2 steps for optimization, and here you try to solve. You do not solve minimize fx exactly, but you try to solve a bunch of sub-problems. Each one has a regularization. The same idea can be applied to sampling. I do not want to sample a point that is far away from my current distribution and far away from the mean of my distribution, but I want to do something in my neighborhood. So this is the idea. You try to regularize the density, again, like in optimization. Here you add a quadratic, and here you subtract a quadratic, because f here is like minus f there. So you subtract a quadratic, and this is the subproblem that you want to solve in sampling. And before that, I want to change my proximal point. Here, changing a proximal point is minimizing some quadratic function. And again, like the translation from here to here, minimize something is similar to sampling from e to that objective. And here, minimizing a quadratic is like sampling from e to the exponential to the negative that quadratic. And this is the step where we change a proximal point. And this is basically a Gaussian step, because this is, if you do normalization, this is Gaussian. So the first step is easy here, but the second step is very challenging. Just like here, in optimization, solving the proximal point method is not easy. That's why we have so many different variants. You need to design iterative method for solving each subproblem. And the same logic applies in sampling. So solving this regularized sampling problem is not easy again, and you need to design some iterative method. And some of the ideas in optimization can be translated there. For example, SGD, so the counterpart of SGD in sampling can be viewed as ULA, and some proximal variant can also be translated into sampling, and that gives you the proximal version of the Langevin algorithm. And the proximal bundle method, it also has a counterpart in sampling. So by doing the translation of the algorithm, you can also bring a powerful algorithm from optimization into the sampling area. And yeah, this concludes the 2 examples I want to cover in the application part. But we will, there are certainly more interesting and important applications in machine learning that uses optimization algorithms. For example, in GAN, in generative adversarial network, people are using the primal dual optimization approach. And in so there is another very interesting algorithm called single-horn algorithm for entropy regularized optimal transport. This one uses the proximal point idea as well because of the regularization part. It's very similar to the idea here. We are regularizing the function and try to solve the regularized subproblem. And in online learning, one of the most famous algorithms, follow the regularized leader, is basically mirror descent. And in reinforcement learning, if we want to do the policy iterate, people have been developing policy gradient methods. Basically, this is very similar to first-order methods in optimization, which are just working with gradient. And there are many more interesting applications that we could cover in the class. And you can also try to explore some interesting topics in your own cross project. I think that's the end of the introduction part. And after that, I will briefly talk about convex analysis and the complexity analysis that is needed in our class. Before that, is there any question? Okay, cool. So
One basic question. So when, in my application area, when we think about sampling, we're always doing it for the purpose of understanding how uncertain the final solution is. So for example, the XK, we say we do not know it. We know that we've solved for XK, but there might be other XKs that solve that problem. That's why we move from optimization to sampling. Is there any other justification for why somebody will conceive of their problem exclusively as sampling rather than just for the purpose of understanding the uncertainty, like measurement error, observation error? Is there any other incentive for rethinking the problem that way, like moving from optimization to sampling?
So in optimization, you design an algorithm, right? It gives you xk in a certain interval k. And you can quantify how good the solution is by measuring this optimality gap, right? How far I'm from the global minimum. And you can quantify this by discussing the complexity. So if I want to achieve epsilon optimal solution, how many iteration Ks I need? And for example, the gradient descent gives you 1 over epsilon. So this sort of gives you how fast this algorithm is, right? This is the speed, the convergence rate, and this is the complexity. And in sampling, you can do the same thing. So the way we quantify is by considering the rho k, because in Rn, if you follow the ELA algorithm, so if you follow this algorithm, you have an xk. The xk, it follows a distribution rho k, just like in continuous time, xt follows rho t. So in discrete time, xk also follows a distribution rho k. And rho k also evolves, right? In the end, I want rho k to be rho infinity. And your goal is to measure how far the rho k is from nu, right? So I want to measure rho k from nu, how far they are. So you can use different, for example, you can use different metric, or even non-metric. It can be a divergence, just some measure, just like a distance between distributions, right? So for example, you can use KL divergence. That is the same thing as this relative entropy. They are the same thing. You can use the KL divergence, or you can use chi-square, or you can use Ranye divergence, or for example, W2 distance, anything that you can measure the distance between two distributions. And you also want, people are very interested in when they are less than or equal to epsilon, when the distributions are close to each other. I'm also interested in when, for example, for KL divergence, I'm also interested in when they are less than or equal to epsilon. And you can also give a complexity guarantee for that one. For many algorithms, this is the focus in sampling, maybe in the recent 8 or 7 years. People are more and more interested in giving non-asymptotic convergence guarantee like this way, just like in optimization. Yeah, so this is another similarity between optimization and sampling. The goal is the same, right? We both want to minimize something, and the algorithm are similar. So from optimization, you can do some translation, but this is not that trivial. After you do the translation, you have some sampling algorithm, and in the end, you also want to have a similar measurement, right? Just like in this way, you want to know the complexity to get epsilon solution.
So as an analytical tool for understanding how algorithms behave
Right.
efficiently. So for example, if I do not know f of x or the gradient of f of x, I can still do that analysis to
Yes.
see the complexity of the algorithm. Thank you.
Yeah, so that's the goal of the class. We do not only want to talk about algorithm design, but we also want to give you a guarantee how fast my algorithm is, does it converge? With that, I think I conclude the introduction, and we can talk about the convex analysis and complexity analysis. Does everyone know what convexity is? What a convex set look like and what the convex function look like?
Not so sure, sorry.
Yeah, no worries. So pictorially, a convex set can be a line segment, or it can be some polytopian high dimensional space, or maybe a ball, right? A ball in maybe RD. So, but this kind of shape is not this one is not convex because if you pick a point here, X, and if you pick another point, Y here, and draw a line segment between them, part of the line is outside the region, it's not in the region. So if the line segment, every point of the line segment is in the region, it is a convex set, otherwise it's a non-convex set. So the definition so a set in Rn is called convex if for any 2 points x, y in S and a scalar lambda in 0 and 1. This is just this is describing the point on the line segment. So any combination of the 2 points is a point on the line segment. If our point is on the line segment, then you'll find this is a convex set, right? So this is x, this is y. If lambda is 0, I'm at the point x. If lambda is 1, I'm on the point y. Sorry, the other way. But for the lambda in between 0 and 1, you are on other points. Some other examples are like, suppose this is a hyperplane in the space, and the half space is a convex set because if you pick any points, they are on the same side, not on the other side. Convex function is something that looks like this. Basically, if you pick 2 points here, any 2 points, draw a line segment, and it is above the function value, right? It's above the function value. Then this is a convex function. Or another way to view this is as this is a function that we know it's a convex function. If you pick any level set, this is a straight line, any level set T. The region underneath, so the region between the level set and the function value, the function, this region. If this region is a convex set, then the function is again a convex function. So the formal definition, we have 2 definitions. They're both true, and you can show one implies the other. So this is saying that just like the picture we showed before. So if you pick any 2 points in Rn, like here we have a point x, y, and consider the function values f of x, f of y, to a convex combination of the two, or any point on this line that is this convex combination, right? It is above the function value of this point. This point is lambda x plus 1 minus lambda y. This function value is this part here, right? So for any two points x, y, and any lambda between 0 and 1, the convex combination of the function values is above the function value of the convex combination of the 2 points. Then this function is convex. That's the definition. So this is definition 1 for convex function. And definition 2. So before definition 2, we need to introduce a notion about so we need to talk about epigraph. The epigraph of f So epigraph is a set of x and t. So this is in the space of R n plus 1. Here I'm not drawing that. Yes, here it is in n plus 1 because this is x. Right? This is your function value. This is another dimension t. So this is a 2D object. Epigraph is a set in Rn plus 1. Here n is 1. So this region is the epigraph of function f. T is this is for fixed t, but this is for any t. So any line, anything above like infinity here, anything below is in the epigraph. And if epigraph is a convex function, is a convex set, then the function f is convex. This is the second definition for convex function. But this is can be shown to, we can show definition 1 and definition 2 implies each other and vice versa. So f is convex if the epigraph, the set, is a convex set. Here are some examples of convex function. This is a linear function or a affine function. It is a convex one because pictorially this function looks like this. Right. If you pick any points, any 2 points x and y, so the convex combination of the function values are exactly the same as the function value of the convex combination of the 2 points. So this is a convex function. Or a quadratic function is also convex. So this gives us another example. So if the matrix A is positive semi-definite, then this quadratic function in X is also convex. This is just a generalization of this 1D function. There are many other interesting convex functions, but I'm not going to cover all of them. I will give you some calculus rules, simple calculus rules that can show you with some basic convex functions, some combination of them, it's still convex. So this is the operations that preserves convexity. Here, X is in Rn space, and A is a matrix from Rn to Rm. This is n by m, n by n, sorry. B is in Rm space. So this is basically a linear mapping, right? And if function f is convex, then this function g is also convex. Another example is a combination of convex functions. Suppose I have a series of convex functions. All these functions are convex. And I have some negative scalars of a 1, of a 2. So here with 1 plus sign, it means everything is greater than or equal to 0. If I write 2 plus signs, it means alphas are strictly greater than 0. So here, if you consider a linear combination, not convex combination, a linear combination, summation of I, Fi, then this is convex again. This can be shown easily by following this definition using the function value. Here comes the interesting operation. So suppose I also have a bunch of functions, Fi's. The Fi's are convex. And I is an index set I. This I, in this case, is just a set of 1 to up to m. But this one could be infinite many, the index set I. So suppose I have all these convex functions, and then if I take the maximum, if I define my function f of x to be the maximum, pointwise maximum, this is again a convex function. For example, in cutting plane method, you will use a few cutting planes. This is a function like f1. This is another function f2. This is f3. Each one is a fine function. So as we mentioned before, it's like example here. Each of them has the form of this one, right? So they are convex functions. And the index set here is just 1, 2, 3. And they want to define the function f like the pointwise maximum of them. So the function f is just this one, right? Because I'm taking the max, this line goes here. I'm taking the max of 1, 2, 3, the 3 function values, right? Each one is the max of the 3. And this is your function f. this one, visually we can see this is convex, right? Because if you draw any two lines, it's about function. So this is another operation that preserves the convexity.
Excuse me, sir. How about the minimum? Minimum does preserve.
Minimum probably will give you a concave function. For example, again in this example. So if you take the maximum, you have this one. If you take the minimum, you got this one. So with proper definition, you will define the minimum operation will give you the concave function. So with this operation, let's see an interesting example that how we can show a function is convex using this rule. So consider a set C. This is a set C. And for a point x, I can measure the distance from my point to the set. This is just a projection. For projection, you find the point, and this distance is defined as the distance from the point x to the set C. And this is the distance function. Here is L2 distance. Right, the distance is just the minimization. I want to find a point in the set C such that the distance between the point and x is the minimum, the smallest one, right? Any other points will have a larger distance than this one. So this is this y, the y is here actually, the minimizer. This distance is defined as dc of x. And now I want to consider another function. I want to consider phi c of x. I'm now considering this function, and then I want to show phi c of x is a convex function. But this may be not that easy to show if you want to show this one by following the definition, the function value, right, the convexity. It's not easy to do that. But with that with that operation, the max operation, we can easily show that. So we first need to do a reformulation. So let's first let's calculate what dc square is. By definition, we just need to square the distance. And then spreading out the quadratic term, we have x squared. Right, any question? This is just expanding the square. Okay, and so if you rearrange the terms, you will see that phi c of x, putting dc squared to this side, putting the max to the other side, and then divide by 2, you will see that phi c right? And so this is a maximum of the maximization is over y in C. C here can be viewed as the index set I there. Y is just an index, just like I there. And the function, in terms of x, view this as a function of x. It is linear in x, right? This has nothing to do with x. This is just a constant for fixed y, for fixed index. This is linear in x. So the function inside the bracket, this part, is convex. And this is a maximization over a few index functions, and each of them is a convex function. So by using the operation that copies the rule there, the maximum, pointwise maximum of x gives you a convex function. So phi c of x is also convex. And the interesting here is to notice that no matter, regardless of c is convex or not, this function is always convex. So c could be some non-convex function. This could be c. And this function is again a convex one. Okay, so this definition.
Would you please explain one more time, how did you reach to that point? The last line.
This line?
Yes.
This is just algebra. So you move this one to the right, move the max to the left. So you have this thing is equal to x squared minus this squared, right? And divided by 2, following the definition here. The definition we wrote here before about the function value and the convex combination, and this one about the epigraph, they do not use any further information beyond function value, right? Here it only involves function value, so they are like a zero-order definition. What if the function is continuous? What if the function f is differentiable? We can use first-order information like gradient. And what if it's second-order differentiable? Then we can use Hessian. So let's give two other definitions. So if f is suppose f is continuously differentiable, so now I can take gradient or take derivative. Then f is convex if the following inequality holds. For any point x and y, my function value f of x is greater than a linearization. So if this inequality holds for any pair x and y, then the function f is convex. Pictorially, this looks like this. This is a function f, and for any point y, this is function value f of y, right? Going through this point and along the direction of the gradient, I have a unique gradient because this is a smooth one. I'm drawing a smooth function here. So going through this is a gradient direction. Going through the gradient direction, I can construct a cutting plane. Right? This is a function, maybe we can call gx. Gx is f of y plus this inner product. It's just a cutting plane, a linearization of the function at the point y. And if the function is convex, the function is always above the linearization. No matter at which point you build your linearization, it's always above it, right? And another definition.
Is it also sufficient or only necessary?
It's both sides.
Both sides.
Both sides. Another definition is when f is second-order differentiable. So I will just briefly write that the hashing exists. When it's second-order differentiable, when it exists for any point x, then the function f is convex. If the hashing is positive semi-definite. For example, the quadratic function this quadratic function, the hashing matrix is just A. So as in the example we gave before, if A is non-negative, if A is positive semi-definite, then the hashing is positive semi-definite everywhere for any x. So it follows from this one. This is a convex function. So I think that concludes the part we want to talk about convexity. This is just a very brief introduction to convexity, but the convex analysis can be a whole subject by itself. Next time we will talk about the complexity notion we want to use in the class. And see you on Thursday.
So all the definitions here are over Rn.
Yeah,
If fx, the domain is fx of a given subset of Rn, do you need x to be convex?
In the domain.
The domain of the function, yeah.
Yeah, if you want to define only on the domain, you need the domain to be
For all the definitions, for basically all the
yes, but here we just do it in Rn for simplicity.
Are you free next week Thursday?
Next Thursday.
Yeah, we have a speaker who's coming from Maryland. He does machine planetary seismology. Yeah, sure. On University. I'm hosting him, so I just wanted to see if I can put you in the schedule so I can talk to you about all the stuff we're doing together. Next Thursday? Sorry, next Friday. Next Friday. I'll send the schedule to you to see what's happening on Friday.
I'm totally free on Sundays. Will be
His talk is typically like 3 o'clock.
derivation.
And then we have lunch, like the students have lunch with the speakers. I don't know if you
Oh,
guys
yeah.
have one.
I'm not sure how many problems
So
I will give, but most of them will
last
be.
week we had another speaker, but she doesn't do what you.
Maybe there will be one problem, but it's not that.
But this one is more like,
be that difficult.
you know, he does like signals, he does investigation.
Python or
Machine learning.
Depends on you. Anyone you want.
So yeah, I'll send you the schedule, just
And by the way, the recording of last class was online
I'm
in
hoping
the
that
course
I
website.
can take some of his
Blackboard.
ideas
Oh,
and
and
generalize it for some other
Yeah.
ones.
or
To have you
I
chat
think
with.
both have been recorded, but at least the last one has been recorded. You can find
I'll send you
it.
the-
Blackboard. Put an announcement there, you can find the sheet.
Things you get out the next class's way. That's great, guys. I'm gonna have to.
Just some function I defined. New function.
This is Highland 203, right?